Welcome back, everybody, to the Python tutorial seminar series. Today, Anderson Banihirwe will be covering Dask, and this is the first of a two-part seminar series on Dask. The second will be on August 11th. This session will be recorded and published. I would like to thank everyone for their understanding and patience when we had to postpone this session previously. Before I begin, as always, I need to review the code of conduct. By joining this Zoom call and participating in the tutorial seminar series, you've agreed to adopt these values and engage in respectful communication only. Any inappropriate remarks will have you removed from the call. The seminar is only an hour long, so if you need help, we'll try to provide it in the chat, but ultimately, if you're having difficulty that needs one-on-one individualized attention, we will be able to provide that for you after the session. So please relax and do your best to absorb the information in time, and we'll catch you up before Dask Part 2. Some learning resources I'd like to direct you to are Stack Overflow, the X-ray documentation, and today's content, which I will post the link to in the chat. It is the same repository as last time. And with that, take it away, Anderson.
Thank you, Julia. Let me share my screen. Okay. I assume you can see my screen. If not, just let me know. Okay, give me a second. Okay, so welcome again for those who were here last time. And for those who are new, I hope this is a useful session for those who are not familiar with Dask, and for those who just want to learn more about Dask. Hopefully there's one or two things to learn today. So the repository that Julia pointed to, so if you've already cloned that repo before, you may have to get latest changes. And on my screen, you should see a few commands that I have that will basically allow you to pull changes that I added since the last time you probably cloned it. So you have to run, so in whatever you clone the repo, you have to run these three commands, which basically they stash your changes that you made locally. And then the git pull command should make sure that you are up to date. And then if you haven't done so already as well, go ahead and run these two commands, so mostly the first one, because you actually want to update your environment just in case things changed since the last time I updated the repo. And then once you're done, then you can go ahead and just launch Jupyter Lab. So for those who don't want to go through this process, so feel free to go to the repository itself on GitHub, and then click on the launch binder badge. That should at least give you a live session in the cloud. It has some limitations because the resources are limited. I think you're only getting, one CPU. So for some of these things, you may want to run this on your own machine. Otherwise, binder should still get you up and running if you don't want to go through the setup. All right, so, well, I'm going to use my local machine for this. Okay. Okay. All right. Wait a second. Okay. Before we get started, so you want to go back to this notebook, the download data notebook. It's under notebooks. So when you launch Jupyter, you should go to the notebooks directory, and then there's this notebook that basically downloads data. So make sure to run that notebook because we use some of these files later. And if you already have some of these files, the function here is clever enough to basically not re-download it if it doesn't have to. All right, so at the end, you should basically have roughly, I think, 6 or 8 files in the data directory. And that should take a few seconds. Okay, so once you're done, now head to the notebooks directory again, and then go to this, so notebook 07, Dask intro. So that's a notebook I'm going to start with. Okay, so I'm going to try to go as slow as possible, but if some things are not clear, please feel free to ask questions in the chat, and in some cases I may even stop and answer those questions if need be. So yeah, so I'm assuming that everyone is ready. So this is the notebook we're going to start with. Let me place the phone here. Okay, so I guess, so one thing that I wanted to start with is, so there's this advice, which I find to be useful. So a few days ago, was someone who posted this on Twitter, and Dask developers reply by saying that basically, if you can avoid Dask, basically go with that route. So if, like, basically make Dask your last resort. Like if there's some other ways to get things done without Dask, it's highly recommended that you basically avoid Dask. And the reason for that is because distributed computing is a bit, it introduces some complexities. So in this case, if you're used to working on your local machine, so you're only dealing with one machine. But then once you start using Dask, in some of these cases, you're going to start working with 10 and hundreds of machines. And that in a way kind of requires a different kind of thinking, because now you're no longer on one machine. So it's basically you're managing 10 or hundreds of machines. And if you can avoid that, then that's probably the best thing to do. But if you cannot, then I guess then we should go ahead and find out what some of these complexities are and what Dask has to offer. Okay.
Anderson, could I just mention something real quick?
Yes, please.
So the data that's being pulled in, the ESGF data servers are down with the maintenance.
Oh. I didn't even check.
So,
okay.
Yeah, so I know that the chat is kind of blowing up regarding that, but yeah,
okay.
so that stems from the servers being down.
Too bad, because I guess I already had copies of this data. Maybe that's why basically my function was just not telling me that things were broken. Okay, we'll have to find a way to deal with that. Okay, well, I guess, okay. All right, so Dask. Okay, so what is Dask? So if you've never heard of Dask, so Dask is a Python library, or it's an ecosystem at this point, because there's a different components that comprises what usually people call Dask. So when you hear people talking about Dask, people may actually be referring to different things. But the main piece is a parallel computing library that aims to scale existing Python libraries. So if you use things like NumPy, pandas, Dask is basically is meant to scale those. So NumPy by default works on a single machine, or pandas. So Dask builds on those to basically allow you to run NumPy on a set of computers that may not be, so a set of processes that may not be under one computer. So in this book, we're going to go through some of the components. So there are two key components in Dask. So there's what they call Dusk Collections, and then there's the dynamic task scheduling. So Dusk Collections, so those comprises of things like Dask Array, which, so you can think of a Dask Array. Okay, we're going to cover this, but you can think of a Dask Array as, in this case, just like parallel NumPy. So you have basically like a bunch of NumPy arrays. And then you have Dask data frame, which is basically like a bunch of parallel pandas data frames. And then you have this thing called Dask bag, which you can think of if you've worked with Python lists. You can now think of parallel or multiple Python lists. And then there's Dask ML, which is a project that is meant to scale scikit-learn if you work with machine learning. So it allows you to run basically scikit-learn in a distributed fashion. And then there's Dask delayed. We're going to cover that. And futures. So Dask delayed and Dask futures, those are low-level collections. And in the next notebook, we're going to cover Dask delayed because it's once you understand how Dask delayed works, you probably understand probably like 60% of what's going on under the hood in Dask. And then Dask futures, I won't cover this because it's a bit more advanced, but I thought I would just mention that so that people are aware of it. So those are the collections. And then there's the task graph. So by default, Dask uses this concept of lazy evaluation. The idea behind that is that usually if you define a variable, right? If you say a equals to 5, by default that is evaluated eagerly, meaning that that variable and the memory is allocated for that. But then with Dask lazy evaluation, Dask under the hood is building a task graph, and then you have to be explicit in terms of when you want Dask actually to do the computation. So the task graph is the key component. And then the last component is what is called schedulers. And the scheduler is basically supposed to execute task graph. So the idea is that the scheduler will build a task graph and then it will talk to different workers and distribute work. And in a way, it will organize these workers and ship work to them by basically looking at the task graph in this case. So we're going to cover that. All right, I need to fix this. Wait a second. Never mind. Okay. So yeah, so here I was just mentioning the difference between lazy evaluation. So with lazy evaluation, like I said before, objects are evaluated just in time when the results are needed. So when you actually need them. Whereas with eager evaluation, once you define that variable, that memory is allocated, and basically things are just done right there. So what are some of the advantages of using Dask? So if you're familiar with NumPy and Pandas, Dask tries to mimic those APIs, meaning that you can just think of like a Dask array as you would think of a NumPy array with a few add-ons. Same thing with Pandas. And then Dask is designed with interactive computing in mind, meaning that it tries to be as responsive as possible. Depending on what system you're running on, Dask allows you to do adaptive scaling, meaning that if you're familiar with other frameworks such as MPI, with MPI, you basically have to think about how much resources you want ahead of time, and then you have to request those resources, and then you go ahead and run your workflow. With Dask, you can actually let the scheduler figure that out on its own, depending on how busy the system is. So I won't cover this here because we don't have access to a cluster that we can use for that, but know that something like that exists. And then also Dask is also flexible in that it has these other projects such as Dask Job Queue and Dask Kubernetes, which allow you to interface with existing cluster resource managers. So if you have access to a system that, let's say, runs PBS or Swarm, you can basically run Dask on top of that, and that would allow you to do the dynamic scaling that we mentioned in the previous point. Okay. So I previously mentioned task graphs, and you may be wondering, what's a task graph? So internally, Dask represents computation with task graphs. So more specifically, directed acyclic graphs or DAGs. And you can think of a task as just like a function. So you just have a function that you want to call, and that function in Dask parlance is basically a task. And then a task graph is just like a collection of those functions with their corresponding dependencies. So in this case, like inputs that go in and stuff like that. So here's an animation of what like a Dask task graph may look like. So the idea being that, so in this task graph, we've encoded the task, in this case, the functions that we want to run and their dependencies. And Dask then goes ahead, when we need the resource, Dask goes ahead and actually runs this task graph. Okay, so that's it for this notebook. So I've linked to some references. So if you wondering like where would I ask questions about Dask and things like that, so I have a few links here and some examples. And then with that, I'll move to the next notebook. Okay. So in this notebook, we're going to look at Dask delayed. And the idea is that we're just going to parallelize like simple for loops. With Dask delayed, we should be able to see what goes on under the hood when it comes to Dask. And that would, and also Dask delayed would, understanding Dask delayed makes it easy to build complex systems, because sometimes you may find that something that you probably want to do, Dask doesn't support that natively, but then with Dask delayed, you can actually build that yourself. So it's a really powerful piece when it comes to Dask. So in this notebook, we're going to deploy a local Dask distributed cluster. Then we're going to look at some diagnostics dashboard. And then we're going to work with Dask delayed to parallelize like a few functions. Okay. All right, so the first thing we're going to do, so let's go ahead and create a Dask cluster or local cluster. So I have a notebook in which we go through, we deep dive into what like a Dask distributed cluster is. But the one thing to keep in mind here is, in this case, what I mean by a local cluster is that, so you have your local machine that has a bunch of CPUs. What Dask is doing under the hood is just launching a few processes. So this is happening here, as you'll see. So if I run this, this may take like a few seconds, and you should see something that looks like this. So we created a cluster by basically saying, oh, Dask, we want to create a local cluster. And then we pass this cluster to the client, and we're just printing the client here. Okay, you may be asking, what's a cluster? So in this case, a cluster is just a set of workers. So think of like a set of processes. And in this case, all these processes are on one single machine. But if you remember what I mentioned about PBS and Swarm, you could actually have these processes on different machines. The only difference is that you basically create a different type of cluster, but then you connect to the client in the same way. In this case, the client is allowing you to basically connect to those workers since they may live somewhere else. This is basically how you get to connect with those workers. So you connect your cluster to the client, and the client is running in the same process as wherever. So in this case, the client is running the same process as where the notebook is running, meaning that wherever our code is, that's where the client is as well. Okay. So if you're curious, you can actually look at the local cluster because you can actually customize this. Like for instance, you can specify the number of workers, how many threads per worker, processes. There's a bunch of other stuff if you're curious. But for now, Dask has some heuristics. When we just call it without specifying anything, it will just look at like how many CPUs you have, and then we'll kind of figure out, okay, how many processes it needs to create and how many threads to allocate. Okay, now if you go back to this cell, there's a few things here. So you see that, so there's a client, and then there's a cluster. So if you click on this, you should see there's basically a drop down here, which will tell you what type of cluster you're connected to. And in this case, it's telling us like a few things about the cluster. So the status, so the cluster is running. We have the dashboard. We're going to look at this later. How many workers, how much memory? In this case, it's just using all memory that we have on our local machine. And we have 12 threads. And then you can look into more information about the scheduler. In this case, it'll kind of tell you more about the workers themselves. So this becomes useful if you have like a distributed cluster on more than one machine, then you may get to see more information. But the experience should be the same regardless of whether you're using like a single machine or a bunch of machines. And then, so one thing that I would like us to look at is the dashboard here. So you can click on this link, which will open a new tab in the browser. And this is where Dask is reporting a bunch of diagnostics about the cluster. So there's the workers. So in this case, we have 4 workers, and they'll kind of tell us how those workers are doing in terms of like how much memory they have access to and things like that, how busy they are, like the CPU usage. And there's a bunch of other stuff here, but you can actually go back to, if I hide this thing. A second. Yeah. Okay. Now you can, if you go back to the notebook, you will see on the left side, there's this Dask logo. If you click on it, you will see a few options here. So you can take this URL, in case these are not active, you can take that URL and then just copy this here, and then just hit enter. Oh no, you need to remove the status. And that will basically activate like a few of these. And what this allows you to do is look at some of these diagnostics under the same tab without basically going to different browser tab. In this case, let's look at a few of these. So if you click on cloud map, which in this case, the middle piece here is the scheduler, and then these other pieces are just the workers. We'll see how that works. And then let's look at progress one here. And there's a task stream. The nice thing is that you can actually tile this however you want. So in this case, you can move these around, which is what I'm going to do because I want to look at these as we work. All right. So that's it about Dask distributed scheduler. All right. Okay. So now let's actually start doing some work. Okay. So what we have here is basically we have a few functions. So you can go ahead and run these cells. So we have 3 functions. So we have this square function, which just takes a number as input. It sleeps for 1 second. This is so that we can actually simulate. Otherwise, this computation is too fast that we won't be able to see Dask in action. And then we return the square of the number. It's another function here that takes in 2 numbers or 2 inputs, sleeps for 1 second, adds those 2 numbers, and then returns that. And there's this other function here that, again, sleeps for 1 second, and then just computes the square root. So now, so I'm using this time magic in notebooks to actually time how long these take. So what I'm going to do, or what we're doing here is we're basically, so we have two inputs, so 3 and 4. We're squaring both of those, and then we're adding x and y, and then we're computing the square root. So this is basically happening. This is happening in serial. In serial. So we're doing one thing at a time. So if you run this, you should expect this to take 1 second, 1 second, 1 second, 1 second. So this should take roughly 4 seconds, as you can see. So again, because we're calling these functions sequentially. But then if you think about it, X and Y, they're independent from each other. Like basically, there's no reason why we should wait for X to finish before we compute Y. So we can basically compute these in parallel. That should at least allow us to run this in less than 4 seconds. So this is where Dusk date comes in. So the way we do it is, so we have our regular functions, but then we have to create what Dusk calls delayed functions. And the way you do that is you call Dusk.delayed, and then you pass the function. In this case, we're basically creating a corresponding delayed square function. Same thing for the add and the square root. And then we go through and we basically do exactly the same thing as what we did before. So as you can see, this just almost runs instantly, 2.8 milliseconds. And the reason for this is that we actually haven't done anything. So the only thing that Dask did is just it constructed a task graph. We're going to see what that looks like. And as you can see, R here is just a delayed object with some ID, which is something that Dask is using to keep track of this internally. So once we actually want the results, we basically call .compute. So what I want you to do is, I want you to run this cell, but at the same time, watch what happens in these panels. So, okay, so one thing that you're going to notice is that this now takes roughly 3.43 seconds, we get the same result. So here's then how you may interpret this these diagnostics. So if you hover, so if you're in the task stream, which if you're not using this, if you're just using the regular tab, if you go to the status, that's the first thing that you see here. So if you hover, this will basically tell you the name of the function and how long it took. So as you can see, we have two square functions. They both took 1 second. And each row here corresponds to a worker. So one square run on one worker. So as you can see, those two run at the same time, right? But then there's the add function here, which is basically a dependency.
Yes. Can you get the Wi-Fi outside this door? I never.
So, okay, sorry about that. So we have the two functions, so square, and then we have the add, which depends on the outputs of these two. And you can see that this add function run on another worker, or at least the same worker that run this function is the same worker that run the add function. And then there's the square root, which run on a different worker. And that is basically Dask taking care of everything for us. We just tell it what we want to run, and then we figure out where it should schedule stuff. So 1 second, 1 second, 1 second, 1 second. And as you can see, if you wanted to, in some of these cases, can use the wheel menu here to actually zoom in. We'll see that at some point, if you zoom in here, you'll see that there's this red here, which is actually the transfer. And the idea being that since this worker needs to add X and Y, and X was run on a different worker, we need to do some communication so that it gets the right dependencies. So this is the red encodes communication. So we had to basically talk to some other worker to be able to get some dependencies that we needed to be able to run this function. Okay, And again, well, this ran too fast, but if you run this again, you'll see that in the Dusk cluster map, you see that basically that's the communication pattern. So you'll see that one worker is kind of talking to another worker. So this worker and this kind of talking to each other. And then in the task stream, on the Dusk progress, what you see here, it's too fast, but you see it will tell you basically the name of the functions and how many of those, and will show you the progress. Okay, so what just happened? Again, Dask built a task graph, and so if you have a Dask data object, you can actually call .visualize on this, and I will actually show you what the task graph looks like. So as you can see in this case, so basically we have our two square functions, which the inputs, so the outputs become inputs to the add function, and the output of the add function becomes the input for the square root function. All right. So by default, so if you wanted to actually render the task graph from left to right, you just call visualize, and then you pass this keyword argument, and it will just render it from left to right. This is useful if you have like a huge task graph that, or maybe you have a wide screen. So yeah, so that's basically what happened. So Dask built this graph, and then when we called .compute, it ran the task graph. Okay, so a few questions, like for instance, why did we go from 4 seconds to 3 seconds? So again, you should be able to get the answer by looking at the task graph. So this function takes 1 second, this takes 1 second, both of these take 1 second. Right? Remember, because these two are independent from each other, we can actually run them at the same time, meaning that eventually we end up spending 1 second doing the square. So 1 second, 1 second, 1 second. And that's how we end up with 3 seconds. And maybe asking basically, why couldn't we get it down to 2 seconds? That is just because after we're done with this, there's no other parallelism. So everything is basically needs to run sequentially because of the dependency. All right. So another question is, what if you basically remove the sleep? You can try this on your own, but what you end up getting is that that computation is too fast, and because of that, actually using Dask makes it slow because of the overhead that is introduced by having to manage different processes and things like that. So if you have computation that is too fast, that's why I say that maybe Dask is actually not going to help you that much. And you might as well just look into other ways to speed it up. So that's one case where if the computation is too fast, you won't really see benefits. Dask is just going to be actually slow. All right. So that was just like a few inputs. So in this case, I have an exercise here where we actually could create a loop, and you can try this. So in this case, we just have a list of numbers, and let's say we're interested in computing the sum. So we have a list of numbers and we want to compute the sum. So the way you would do that, okay, and we basically want to compute the sum of the squares. So the way you would usually do that is you just loop through these numbers, compute the square for each number, aggregate or accumulate the squares in a new list. And then once you're done with the looping, and then just compute the sum. So roughly this should take, since we're sleeping 1 second, this should take roughly 10 seconds. I think. Okay. So yeah, so this takes roughly 10 seconds. And so the sum is 385. So how would we go about parallelizing this with Dask? Again, if you look at this loop, there's no data dependency. Basically, each element can just, we can compute the square of each number in this list, independent from each other. And this is where Dask really becomes very useful. So yes, I provide a solution, but I was going to say, let's try this as an exercise, but I actually have the solution here. So if you look at the code here, the only thing that we really need to change is just instead of calling the square, we just call the delayed square function. Sure, we've been here. And the code is exactly the same, except that at the end, we also wrap sum. So we make also sum a delayed function as well. And then once we're done constructing our task graph, then we can actually call it compute. So we should get exactly the same outcome, except that this should actually be faster. So this takes what? This takes 1 second. And you have your answer here, because you can see that all those square function calls are just happening at the same time. So we're not really doing this sequential. We're not relying on, there's no dependencies. So we can just run this in parallel. And that reduces our time to 1 second. And we're getting the same outcome as before. Right, okay. So one interesting exercise would be to look at what the task graph looks like. So in this case, if you take, let's say, square 1, and then you add square of 2, how does Dask actually construct the task graph for that? So we can try that, and what we'll see is something that looks like this. So square, 2 numbers, so square of 1 and square of 2, and then the plus sign here, which translates into add function, which is the built-in add function in Python. In this case, the Dask delayed knows what to do. So that's what, in this case, adding 2 numbers or 2 squares looks like. But then what does the sum look like? The sum that we computed here. So if you're to look at this, oh, actually, okay, never mind. Okay, this is different. So results. Oh yeah, so results is just a list of. Let's actually look at this. So if you print results here, it's just a list of delayed square function calls. And if you call sum on that list, that should also give you a delayed object. And then if you call that visualize, you see what Dask is actually doing under the hood. So you see that in this case, Dask is doing an accumulation. So it's starting, so the first number, square that number, and then in this case, so take another number. So let's go back here. So take 1, square that, plus the square of 2, like so and so on, and you'll see that that's reflected in how this task graph looks like. And the reason for that is because we didn't actually call. Oh man, okay, that's a long. We didn't delay sum, but then Dask still kind of figures out what to do in this case. But then if we delay sum, you'll see that we get a different type of graph, which that's what we should get if we run this. So in this case, because sum is also delayed, this is what the task graph looks like. So we have 10 numbers that we're squaring, and the squares, they go into the sum function. So yeah. So that's how you would, if you have like a list of things that are independent from each other that you actually want to parallelize. It's just as easy as changing, because as you've seen, the only thing that we changed was instead of calling square directly, we're just calling the delayed equivalent. Okay. Okay, one more thing here. Okay. So in the previous examples, or in the previous example of a loop, we didn't have any conditions. So we say we have a list of numbers, call this same function on all those numbers. But then things get a bit tricky if you have some control flows. So in this case, you have like if condition and stuff like that. So we're basically going to do the same thing, except that this time we introduce a new function, is even, which again, so the function is just checking to see if that number is divisible by 2. So we have our same, so we have our original list of numbers. But what we're going to do is, so as we loop through these numbers, let's do this for now without Dask delayed. So what we're doing under the hood is, so we're looping through those numbers. We're checking to see if the number is even. If the number is even, then we double the number. And if it's not even, we square the number. And then at the end, we compute the total. So this again takes 10 seconds because we're running everything sequentially. But then how would you do this? How would you do this with Dask delayed? Well, so you could go back to what we did previously. So just delay the functions themselves. But then one thing you're going to notice is that Dask is actually going to complain. In this case, it's complaining that truth of delayed object is not supported. So basically what's happening here is that we're trying to delay the is even, but then if you think about it, because of this control flow, we need to know basically what this is before we decide what to do afterwards. So there are things that you cannot really delay because you need to know those things ahead of time so that you can decide what branch to take in your code. So in this case, we cannot really delay is even. So is even in this case, we need to run it eagerly. So if we remove that delayed call and we run that, things should work. And what you're going to notice is that we no longer just have squares, we have actually like a mix. So for some of these numbers, we're doubling them. For some others, we're just squaring them. And then whatever comes out, we're just computing the sum. So we can do this again. So this takes roughly 1 second again. So what did we just see there? So one, you cannot delay everything. Not everything is if you're using Dask delayed, the things that you cannot delay because you need to know some of these things ahead of time. So things like, so if you're using if conditions and things like that, you may have to find other ways to delay those. So we saw what happens if is even is delayed. Actually, basically Dask throws an error, says that it doesn't know what to do next. So that's the gist here. Know that yes, you can use Dask delayed on custom functions, but you have to be careful about what kind of things you're delaying, because some of these things may not. You may need to know these things ahead of time. All right. I don't know if I have any questions. So the section here is basically using Dask delayed, but then since we're using the data files, but since the servers are down, I'll probably just show you what this looks like. But you might have to wait a few days before the maintenance is over.
I threw a fix in the chat, basically replacing which data node it's pulling from. And
okay.
It's on GitHub too.
Oh, so okay. Thanks.
Yep.
Okay. All right. So I'm going to run quickly through this example, but if you have questions, then we can address those after. So the idea here is, so if you go back to our notebook, we basically have to our data, we have, so if you look at this variable, we basically have 4 files, which corresponds to 4 ensemble members, and they all span the same time period. And what we're going to do here is, so we want to compute, if you remember in the XRA tutorial, okay, for those who were not who were not at the XRA tutorial, this may be confusing, but so in the previous XRA tutorial, we learned how to compute anomaly. So in this case, what we're going to do is do the same type of calculation on each one of these ensemble members, independent from each other. So basically, we have a list of files, and for each one of these files, we just want to compute the anomaly. So the way we do that is, so I just, in this case, I'm just getting the list of all those files. So I have 4 files, as you can see. And if you look at one of these files, which I'm opening right here, so you see that, so that those are the dimensions we have. And this is the same anomaly computation we did last time. So we group by, so we're computing monthly anomaly. So we're grouping by month, and then we're taking, and then we're removing the, so yeah, we're moving the mean from the original data. So what we get is something that looks like this. So it should have the same dimensions as the input, except that we basically removed the climatologies. And then if you look at one time step, actually one grid point, that's what the anomaly looks like at this grid point. So what do we want? So in this next cell, what we're doing is just looping through each one of these files, doing exactly the same computation. And then at the end, we're putting all these ensemble member anomalies in one XArray data set. So that's the code here. Basically, at this point, we've computed all the anomalies for each one of these files. And I'm just putting them in one data set so that we can easily visualize these. So if you run that, so we're going to loop through each one of these files. And at the end, here's what we're going to get. Give it a second. Should be done shortly. Okay, so this is what we have. So it took 20 seconds. And now we see that we have our new data set has a new dimension, the ensemble member. And that corresponds to our 4 ensemble members, right? Now we can actually look at the anomalies at this particular grid point for all the ensemble members. So this is the code. Again, if you've attended the XArray tutorial, this should look familiar. So that's what the ensemble anomaly looks like at that particular grid point. Okay, so if you think about the code here, it's just looping through files, and there's no data dependency again, meaning that we should be able to do this in parallel. So we should be able to look at all these 4 files in parallel. And this is something that Dask makes very easy to do. I won't go through this, but the only thing that we basically have to change is when we open the data set. So we just wrap the XArray open data set into a Dask delayed call, and then everything else stays the same, except that by the end of this loop, we don't actually have anything computed, meaning that we actually need to tell Dask that we actually want to compute things. Because at this point, at the end of this loop, we only have a task graph. And this is where that's being done. So we're calling Dask.compute. So this time we cannot call, we won't be able to call .compute, because what we have here is actually a list of delayed objects. So we actually use Dask.compute, which takes in a list of things. And then we do exactly the same thing as what we did previously to construct the final data set. So if you look at this now, if you pay attention to the task graph or the dashboard, you'll see what's happening. I think it's actually done. So something that took 19 seconds now takes 8 seconds, as you can see. So you can actually look at the task stream here. You see what's happening in each one of these as well. Again, you can zoom in if you wanted to. So open data set, computing the mean, and then doing the subtraction here. And we can check to make sure that we're getting the same thing by just doing the plotting. So we have exactly the same thing as what we previously had. If you look at results, it's just a dictionary of delayed objects. And we can look at each one of these. So in this case, since this is a dictionary, I just grab one key, which gives me the delayed object, and then I can do the visualization on that. And this is what is actually happening on a single file. So we open the file. The get attribute here has to do with the selecting the variable and things like that. And then there's the group by. We compute the mean, and then we subtract this mean from the group by here. And then we have our anomaly. So this is what that looks like for a single file. So I guess there's a few questions to consider. Is this the kind of speed up that you would expect? So it used to take 19 seconds to process 4 files. Now it's taking 8 seconds. So in this case, that's roughly, so 19 divided by 8. So we basically cut our runtime in half. So is that what you'd expect? Well, to answer that question, you probably have to look into exactly what's going on in each delayed call. All right, so that's it for Dask delayed. So now that we're done, basically we can close our cluster and our client. With that, basically, I will close the segment about Dask delayed. And if there are questions, then I'm happy to take those. So yeah. And if you want to learn more about Dask delayed, if you run this cell, there's a linked YouTube video which goes into a few more details. If you want to try that on your own. It looks like we're running out of time, so I can take questions. I thought that I was going to go through the Dask delayed, but I think that's probably like a topic for another day. Okay.
Thank you, Anderson. Thank you so much for attending. We do have a few questions coming in the chat.
Sure. Let me actually. Okay, chat. Zoom. Okay. I lost my controls. Could you read the questions for me, please?
Okay, our first question, sorry, the chat keeps moving. What would happen if you had more files than helpers, say 12 helpers and 36 files? This question is from Patrick.
Could you repeat that again? So if I had what, 12 files?
12 helpers and 36 files.
So I'm assuming by helpers you mean Dask workers. Is that right?
Yes.
Okay. So basically, under the hood, Dask is taking care of the scheduling. So on your end, you don't really have to worry about changing anything. Dask will basically figure out how to do the load balancing on the Dask worker side. Because at any point in time, again, if you go back to the dashboard, you see that there's a few diagnostics here. So like how much memory, basically the CPU usage. So Dask internally is monitoring these things. And as it dispatches work to workers, it's looking at those things to figure out basically who's busy and who's idle. So on your end, you don't have to change anything. Dask will basically do its own thing under the hood.
Mm-hmm.
We have a couple raised hands as well. I think Stephen is first. Stephen Yeager. I don't know if we have permissions to allow Stephen to unmute himself and
Yeah,
ask a question.
Okay, participants should now be able to unmute themselves, but don't all do it at once.
Thanks. Yeah, my question was in the last example, why you do Dask Delator on the open dataset call and you didn't use it on any other functions like the group by or the mean.
Okay. Is that it?
That's it.
So the reason why I didn't do it, okay, I think this is the code section here. Okay, so the reason why I did it is once you call Dask delayed on a function, in this case, what I'm getting back is a delayed object, which I can manipulate that object as if it was just a regular. So if you actually look at this, let me show you here. Let's do DS. Let's see if this actually. If you look at DS here, you see that DS is just saying it's a delayed object, but under the hood, if you expected, so in this case, I expected this to be a data set, I can just do regular stuff. So in this case, I can do something like this. I can do, say, attributes. So I can do anything. So in terms of accessing methods on that object, I can just do it as if it's just like a regular object. And Dask will actually proxy or will actually delay these things. So it won't do anything. So as you can see, I don't actually get the attributes. I just get a delayed object. So as long as I keep chaining things on this delayed object, I should keep getting delayed objects. And because of that, then I don't need to basically delay these other things because I'm just accessing methods and attributes that are on this original object. But this would change if, let's say, I have like a custom function that I needed to, let's say, there's a function that I need to pass DS2 to do something internally. I would have to delay that function because Dask doesn't know what to do in that case. So I'm just taking advantage of the fact that everything that I'm doing from here on is just using attributes and methods on what is returned by this thing here. I hope that answers the question.
Yeah, that's great. Thank you.
Yeah.
There is another question about can you have multiple clients using a single cluster? That's from Daniel Marshall.
Yes. So okay. So if you go back, so okay, the key piece here is so this cell here. When we create a client, we connected to a cluster. But if you look at actually the cluster here. Never mind. Give me a second. Cluster. So if you print the cluster, you see that it actually has an address. So if you knew what the address of the, so I can create it, say, client2 equals. If I knew what the address of the cluster was, I can actually create that client explicitly. And in this case, I basically have two clients. So there's this client. If you actually look at the ID of this client and the one that I think in this case, it's actually, yeah, let me think. Because I think this is the same notebook. I think this is just pointing to the same client, but I could basically, let's say, go to another notebook and connect to this cluster that I created here by just pointing it to the address. So you can basically at any point, you can actually have multiple clients pointing to the same cluster, if that makes sense. And those clients don't have to exist in the same notebook, in the same script.
Okay, there's another question that I think related to that, I'll just add that the Dask lab extension that allows you to put those little tabs and windows up, that one right there, that can only connect to one cluster at a time.
Yes.
So keep that in mind if you're creating multiple clusters, but you can create multiple clients. to the same cluster. And then there was a question here. It says, I realize that NetCDF4 library is faster when used to read NetCDF files compared to Xarray. Please, I would like to know whether one can use Dask to speed up the read processing time.
Yes. So I guess, so one reason why Xarray is going to be slower than using the NetCDF for Python is that Xarray is doing more stuff. Once it reads the file, it's also constructing these other objects. And if you basically wanted to bypass Xarray and just go directly to NetCDF for Python with Dask, all you have to do is just wrap the open dataset calls from NetCDF for Python in Dask delayed. And that will basically give you something that you can assume that it's whatever the NetCDF for Python is giving you back. So in this case, it would be a NetCDF dataset, I think, object. Then you can just manipulate as you want. But if you go that route, I'm pretty sure you know that you then lose like a few other things that Xarray is providing. But yes, you can do it. You just have to wrap those functions into Dask delayed.
Yeah, and the things you get, the advantages you get from using Xarray are that it double checks and makes sure that all of your axes are consistent across all of your files when it aggregates them into one data set and things like that.
And also once you, we didn't cover this today, but we're going to cover Dask array. So once you start wanting to work with distributed NumPy arrays, at that point, Xarray is probably your best bet here because it knows how to interface with Dask. And if you're to go with NetCDF for Python, I think you'll have to do the, you basically have to manage that yourself, if that makes sense. So we have a few notebooks in the next session that covers Dask and Xarray together. So you don't have to use Dask delayed unless whatever you're trying to do is not something that is prior to Xarray. And so in that case, you get huge benefits since some of these things are really well optimized and you don't have to build them from scratch.
I'm a little concerned that I've missed some questions in the chat. So if people have questions that are lingering and haven't been answered, please repost them. Supreet asked, when would you use the Dask decorator, such as the Dask delayed decorator, and how to use? Could you just give one simple example?
Okay, so what Supreet is referring to, so if you go back to, okay, this section here, you'll see that the way we created this, these delayed object is by calling the Dask delay. So the reason why I decided to go with this approach is that it's more explicit for people who are not familiar with Python. But another way is if you actually wanted to skip this step, meaning that if you didn't care about the original function, you can actually come here and it's just, you just do this here. So at the end, what that does is it will actually create delayed objects for you. So define your function as usual, and then just use this at syntax dot delayed, and Dask will basically take care of, or Python will take care of everything. So under the hood, Python is basically doing this, except that you won't have a reference to the original function anymore. So at that point, you only have the delayed. You only have one reference to just the delayed object. So yeah, thanks for asking, Supreet. Yeah.
Right, so that's not something we've covered in our past Python tutorials, our decorators, but that pattern, the decorator pattern, for those who are curious, is fairly simple. Just think of a decorator as a way of modifying a function. So in exactly the way that Anderson showed it there explicitly, lower down in the notebook, the Dask delayed is a function that takes a function as input and returns a modified function of So that's essentially what a decorator is, and that syntax that Anderson put above is a simple way of applying it automatically to that function. And another question, how do you lay down two open tabs like Anderson is doing?
Oh, you mean these? Okay. Yes, I'm assuming you're talking
So
about.
if you're using Jupyter Lab, this is a feature of Jupyter Lab, and it's covered in the Jupyter tutorial as well, but Anderson can quickly demonstrate because it's pretty easy.
So yeah, so in this case, you just click on whatever tabs you're interested in, which they'll start popping up there. And then if you actually click and hold, you can start tiling this. You can basically move it around, and it will kind of show you where. So yeah, that's how you do it basically. So you just go to the Dusk extension, click on whatever tabs you're interested in, and then just start moving them around. So click on the tab title, in this case, this one here, and then just hold, and then just move it around.
And that's true for notebooks as well. It's true for any tab that you launch.
Yes.
So you can display two notebooks right next to each other. You can move things around in the Dask Lab workspace, however you'd like.
Yeah. Any other question?
Okay, I think that's all. Thank
All
you
right.
again, and we will see everyone in 2 weeks on August 11th.
So for those who are here today, so yeah, next time make sure to run that notebook before the tutorial. That way you don't have any surprises. And I don't think I won't change anything between now and August 11th. So yeah.
And thanks, Max, for that quick fix to get it working. I hope everybody was able to actually download the data before we got to that part in there. I think Max worked pretty quickly to try and get that fix in place.
Sounds good. Thanks, everyone.
Take care, everyone. See you in 2 weeks.